Have you ever wondered how things formed? Or how can two materials be formed into new materials? For example, how does iron rust? Why does the candle burn? Or how does a fruit ripen? What do you think? Everything that our eyes can see, and even the things that are only visible through satellites, telescopes, microscopes, and the likes, are formed through infinite chemical reactions.
But what does chemical reaction means? Chemical reactions occur everywhere around you, and not just in chemistry labs. Chemical reactions cause chemical change, which only means that substances interact and form a new product. For instance, this illustration. There are two substances A and B that reacted with each other and gave us another new substance C and D. We called A and B as the reactants, and the new material formed C and D are called products. Or simply, we can say that these reactants react to form products. These representations of chemical reactions in which the reactants and the products are expressed in terms of their respective chemical formula are what we call chemical equations. In order to have a new form of material out of a chemical reaction, the elements must balance, and we can do that by changing the coefficient of each term in the equation.
But the million-dollar question is, how do we balance chemical equations? Most of the chemical equations can be balanced using a simple approach known as balancing by inspections. For example, this combustion methane. The reactants are those that will undergo reaction, and the products which are caused by the reaction that took place along with their corresponding numbers of reactant and product are shown by the coefficient that is placed on the left side of the elements. Take note that if the coefficient is 1, it can be omitted. Let's take a look at this table. To compute the reactants for carbon, we multiply its coefficient 1 and its subscript 1, then we get 1. And to compute its products on the right side, we also multiply its coefficient and its subscript to get 1. We can see that the reactants and the products were both equal to 1, therefore, it is balanced. The same process will be applied to the other elements, which all resulted in a balanced equation. When balancing through inspection, if one sees the imbalance between the reactants and their products, it is a must to add integers until the goal of balancing the equation is attained.
However, why do we need to balance a chemical equation? Balancing chemical equations uses methods to preserve the chemical compound correctly. It is necessary whereas mass is conserved in every reaction. It is important to balance the chemical equation to see the quantitative relationship between the reactants and the product. Let's look at this another sample equation. In order for a burning propane gas to form carbon dioxide and water, the propane needs to combine with oxygen. This is represented by this equation. It seems complicated, right? If we use balancing by inspection, it might be difficult to tell if the equation is balanced. So, is there any other way? The answer is yes. To help us in computing this equation, we can use the Diophantine equation. But first, let's define what is Diophantine equation.
Have you seen this mathematician? Yes, you are right. He is Diophantus of Alexandria. He's known as the father of algebra, who published the book Arithmetica, the Porisms, and a lot more. He contributed greatly to number theory and mathematical notation. His Diophantine equation is a type of equation requiring an integer solution. Its goal is to seek integer solutions for all the unknowns from the equation. Some types of Diophantine equations are linear, nonlinear, and a special type which is Pell's equation. It forms the central part of number theory, and this means that Diophantine equations can also be used in chemistry since it is necessary for a chemical equation to have integer coefficients.
As we go back to the equation, we could say that it is not balanced. To balance it, let's identify first the elements of the equation. Rewrite the chemical equation into a system of linear Diophantine equations like this. Since we want to find the integer coefficient that would balance the chemical equation, this will become the unknown in the system. Thus, the number of the term in the chemical equation will be equal to the number of the unknown in the system linear Diophantine equation. From this given, assign the unknown coefficients x sub 1, x sub 2, up to x sub n of each element such that a total number of atoms of carbon, hydrogen, and oxygen on the left corresponds to the atom on the right. Now, we have. Using row reduction, we can reduce the variables and get the general solution. So, in order to form a row reduction, the first non-zero entry of the row matrix should be one which called the leading one variable. Inside the matrix, these leading variables should form a diagonal 1 and all the other entries of the column should be 0. To satisfy these conditions, we can use three basic row operations, which are type 1 or the interchanging rows, type 2 which is demultiply the non-zero number to a row, and type 3 which we add a multiple of a row to another row. For this matrix we can apply type 2 operation to row 1 to make the first non-zero entry a leading 1, and type 3 operation to row 2 to make all other entries in first column is 0. For the second row, we can interchange row 2 and row 3 and also use the type 2 operation. To make the entries below the leading 1 variable, we can apply type 3 operation to row 3 and row 1. Here we see that we already have the diagonal leading 1 variable and its entries are just 0. Now, the system of equation is reduced to. As you can see here, we have a free variable or a column that doesn't have a leading variable. And since the coefficient of the equation requires an integer value, let x sub 4 equals integer 4. In this case, we'll get this. Note that the equation can be also balanced if the free variable x is any number k such that k is an element of n. But most chemists prefer to use the smallest possible whole number coefficient in balancing equations. Therefore, the free variable x sub 4 equal to 4 is a possible choice. Now, the balanced equation becomes easy, right? So, let's have another example. How do we balance gunpowder combustion? In this, we have this equation. Just like in the first example equation, we have to identify the elements and assign their own coefficients. We can now use the row reduction to get the general solution. Now, the system is reduced to. And we get this free variable x sub 6 which will be multiplied to a smaller integer to get a whole number coefficient. Here we get a balance equation of gunpowder combustion. Easy to understand, isn't it? With the use of this method, the chemical equation can be balanced skillfully. Since chemical equations seek for an integer solution and it can be written into the system of linear Diophantine equation, thus it is one of the right methods to use. In our everyday life, we encounter natural changes such as digesting our food, the explosion of fireworks, photosynthesis, and a lot more. It is important to understand how these interesting things work in our natural world. Math is everywhere, and so number. It is the language of science that expresses our understanding of what we observe through logic and calculations. See? That's how amazing the world of science and math is.